Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks from Washington University. This is Module 3, which is showing you TensorFlow and Keras. This is part 2, where we actually get into TensorFlow and Keras in Python. Okay, TensorFlow is a Google product. I've given you a variety of links. This is from the course module information. I give you a link to the Google homepage, to their GitHub repository, their supports, and their frequently asked questions. Versions of TensorFlow tend to be very important. This is a comic that I found actually on Twitter by one of the Google developers. Does your car have any idea why you pulled over? Basically, it is, does your car have any idea why my car pulled it over? Basically, it's talking about you have to have the same version of TensorFlow for the class or you're going to have some problems with it. So it's important to know what version you have. I have a little bit of code here. This is similar to the code that you probably ran when you actually installed TensorFlow, but I can run it and it will print out the version of TensorFlow that you have. Installing TensorFlow, I give you a variety of ways to do that, and I have links to videos that I created to show you a variety of different ways that you can install TensorFlow and get to a Jupyter notebook like I'm running here. Why TensorFlow? It's supported by Google. It works well with Linux, Mac, and Windows. It has excellent GPU support. It uses the Python programming language for its interface, and Python is extremely popular in the data science and artificial intelligence communities. There are other deep learning tools. I show you a variety of them here. Thano has actually gone somewhat away. They're still bug supporting, but they basically said that the others are doing well enough that they don't need to be releasing their own library anymore. Right now, the big ones are TensorFlow, MXNet. Keras actually depends on either Thano, MXNet, or TensorFlow. So Keras is just a higher level abstraction. Paddle, Deep Learning for J, Microsoft's Convolution Neural Toolkit, and also H2O. So two of these are Java-based if you're very interested in using Java with this. TensorFlow is essentially a compute graph. So you build these compute graphs. It's really pretty similar to what you do with Apache Spark. You're basically this is basically what you see here, a compute graph for a very simple single layer neural network. It shows you the gradients so that it's training, and this is all part of the training process. It shows you that it is a classification neural network because it's logistic regression. And this is essentially a compute graph. Very rarely do we deal with these. We're going to let Keras do this for us, at least in this class. And then if you expand the deep neural network, because this is talking about how to grade it and everything else, this is just the neural network, you can see the layer 1, layer 2, layer 0, and all of the other parts of this. So TensorFlow works by compute graphs. Here I am showing you something that TensorFlow is capable of that has nothing to do with machine learning. This is very much based on an example that I found on how to use TensorFlow to calculate a Mandelbrot. So if you take this and run it, it will produce a Mandelbrot plot. You might have seen these before, but this is a Mandelbrot set. You could zoom in on any area of this and keep zooming and zooming and zooming and get more and more detail, infinitely deep. It's a fairly fascinating technique. I won't go too deeply into how a Mandelbrot is calculated, but essentially it's a complex number over that forms a plane. So for all the x's and y's, you're essentially calculating what is z, and you're looping over the whole entire plane, and you're running it a number of iterations. Here, I just hard-coded to 2 to get it to essentially converge to this. So if you run it, this is actually very rapid to produce the result. I remember when these first started being used by computers in the 80s, you would run your computer for days to produce a plot like that. But if you don't do as many iterations, it'll be quicker and less accurate. So there you can see I decreased the iteration count. I'll leave it back at what I originally had it at. So this is just showing you this little bit of code. You're creating a compute graph, and you can do something relatively complicated or complicated looking, because the code behind a Mandelbrot is not that complicated. Let's look at a very, very simple case of using a pure, straight-up TensorFlow compute graph. What I am doing here is essentially creating two matrices, two matrix constants. So notice how the square brackets are going. That is a vector, so a 3 and 3. But then I also put one of these around it. So this is a matrix. This is a two-dimensional array that just so happens to have one row with two columns. So this is what you often call a row matrix. This is a column matrix. You have two vectors which both have just a single value stacked on top of each other. So this first one is a row matrix. The second one is a column matrix. And then we're going to multiply those together. Now, these three all together are just defining a graph. They're not doing any computation. When you run it, it is going to give you I guess this is a scalar matrix, because it is a matrix. It's 2D, but there's only one value in it of 12. And that is the output from this. That is what happens when you multiply this row matrix by this column matrix. The result doesn't happen until you actually run it. This part here is essentially compiling. You're creating your compute graph. TensorFlow will take that and compile it for you into highly optimized code, and then you later execute it. Now this program is completely determined. It's only constants being multiplied, so the output is always 12. But you can put TensorFlow variables into here. To do that, notice now we put in a variable. That variable is a vector, and we have a constant. We are basically going to now subtract two vectors from each other. One is variable, one is constant. So we initialize it, and because you have to initialize the variable so that it starts with its initial value. And then we define the subtraction. The subtraction is the root node of the graph. The graph is now basically created at this point, and we can print out the evaluation of it. If we evaluate it, it's going to be -2, 1, which is those two subtracted from each other. Now we're going to assign new values to x. So we're going to do x.assign and run it. And now we get a different value. So this is what you would do for a compute graph. You would probably assign variables to hold your inputs so that you could change them and send new values into the neural network. While you're training it, you would probably assign your weights to variables as well so that you could vary them. And you just create this sprawling compute graph that is the calculation of your neural network. Finally, when you're done with it, you close the session. So up to this point, we have created TensorFlow compute graphs. We have not used Keras yet. This is TensorFlow in its pure form. Keras is something you put on top of it to put all those weighted sums that make up the neural network and other calculations used to train them, and automatically build all these compute graphs for you for neural networks rather than you having to laboriously do that yourself. Now, if you're working in a very research-oriented mode and you want to create a new type of neural network that's never been seen before, you probably will be dealing with the TensorFlow compute graph directly. But for this class, we will be making use of Keras. So for Keras, I give you some, I call these the helpful functions for the class. These are functions that are provided to you. We will see more about how these functions were actually constructed when we get to the data pre-processing step class. But for now, I give these to you all ahead of time. You'll see them at the top of just about every class session. These are just reusable functions that we use. The first time I taught this class, I slowly revealed this to you as we went through. But the problem with that is I had about 8 or 9 different copies of these functions floating about, and students were using the wrong version at the wrong time. So to keep it simple, we have the same helpful functions for all of the classes. You want to make sure that you run this anytime you're using one of the class examples and you see this at the top. You need to run this, otherwise they won't be defined. So it assigned it a number. It's been ran. So let's look at a really simple TensorFlow Keras example. We're going to create a neural network to predict how many miles per gallon a particular car will get. This makes use of the miles per gallon data set that we saw in a previous module. This is a bunch of cars from the US from the 1970s, I think 300 and something of them. And it gives you different statistics, or different data points, like how many cylinders it has, what's its acceleration, how heavy is the car. And from all of these, you would like the neural network to learn how to predict how many miles per gallon that particular car will get. Well, this code that we have here sets up a miles per gallon TensorFlow neural network. These are just the required imports that we have. You'll see these often. Those are the Keras ones. We're importing Panda. We don't really need requests. I must have copy and pasted that into there, but these are the other ones that we have. We will need requests later. We create the file name. We're going to open AutoMPG. We read the CSV file in. We get the names of all of the cars, and then we drop that column. The names of the cars are things like Chevy, Malibu, just different types of car. So we can't really predict anything from the name. We will learn how to process text later. We fill in any missing values in the horsepower with the median of the horsepower. Horsepower does have a few missing values. So anytime you're using the miles per gallon data set, make sure you have this line in it. The 2xy function is very important. That splits your predictors from what you're trying to predict. It creates 2 matrices. So you're going to have a matrix, the x on one side, that is basically showing you what the output of the x is the input. So those are the values that you're trying to predict. And then y is what you're actually predicting. X is the predictors used to predict y. So y becomes the miles per gallon, and x becomes the inputs to figure that miles per gallon out. Then we create our neural network. All neural networks in Keras are created using this class sequential. Even the ones that are not so sequential, they're all sequential. And then we add a variety of dense layers. These are fully connected. Dense means every neuron in the previous layer is connected to the next layer. And what it does is it calculates the number, so it becomes the neural network. The input is however many inputs you had, which is however, I don't remember, there's about 8 or so in the miles per gallon. And that's connecting to 25 hidden neurons, and then 10 on the next level. The activation for both of these is ReLU, rectified linear unit. And then the output. You only have one output because it is a regression neural network. We compile it, that builds the compute graph. We tell it that we're going to evaluate the error using something called a mean squared error. MSE is what you usually use for regression. And then we fit it. Fit means train. We run it, and we're going to give it 100 epochs. So you notice it loops through all of these, decreasing the error or the loss all the time, gets better as it trains. And you now have a trained neural network. You could query it. By the way, you can't, this verbose parameter that you pass into this when you train, verbose equals 2, that displays summary output. You can also display a progress bar, or you can have no output at all. Just different options for you. Now we can predict those cars that we had trained the neural network for. If you run it, it gives you these outputs. These are the miles per gallon that it's predicting for each of the car that it trained with. We can also calculate how good we think the prediction is. So root mean square error is a common error measure. This just means on average, it was off by 3.9 or about 4 miles per gallon per car. It's probably not terrible, but that is a decent number of miles per gallon. If it was predicting the price of a house, $4 would not matter all that much. For a car's miles per gallon, it matters a little bit more. It's pretty impossible to get this, to get the AutoMPG data set to predict with perfection. And here I show you basically how you can loop over, and we're basically just printing out the number, the car name, what it should have been, and what was predicted. So on this one, the car really did get 8 miles per gallon. The neural network predicted that it would get 14. Here the car got 15, neural network predicted 13. By the way, a common problem that students will sometimes have and ask me about is they will say that their neural network is always predicting the same output no matter what they give it. That basically means that your training data or the way you set the neural network up, it's basically just giving up and giving you the average miles per gallon or the average value for your entire data set. If I went back up and changed you can definitely try this, and change the hidden layers to almost nothing and didn't give it any time to train, it would probably start outputting a value that was close to the average MPG. Let me show you how to create a classification neural network. So a classification neural network, the iris data set is a good example of that. There we had the iris flowers. Let me just show you that one real quick. So this is the CSV file for it. So you've got these 4 measurements, and you're trying to predict the species. There's 3 types of species. That's an iris setosa, an iris versicolor, and an iris virginica. The input size, this is very similar code to regression, a little different, but this is all the same. The input size is going to be the shape of the X data coming in. So it's going to be 4 in this case because you have 4 inputs. We have a dense layer with 50 neurons connected to a second hidden layer with 25. Rectify linear unit on both. Notice the output, though, is softmax. And it's the shape of the Y. The shape of the Y in this case is going to be 3 because we have 3 classes that we're trying to classify in. Rather than using mean square error, we're using cross entropy. So these 2 lines right here are really what makes it classification instead of regression. Make sure that you use the correct neural network type for your data set. I have answered many questions by students where they're trying to use a classification neural network for a regression problem, or worse yet, they copy this line. They maybe use softmax and then evaluate it with mean square error. So they have kind of a hybrid of classification and regression, which you would never want to do it that way. Then we train it. We train it for 100 epochs. Does just like the other one. It goes shooting through 100 epochs. This is pretty inefficient, but we'll learn a better way to do it later. And there I just print out to show you the iris species that I found. When you encode a species like that, you can get a list of the classes that it found. And here we predict it. So now the predictions show you the probability. We have 3 different classes of iris. If you look at these, unfortunately they're all in scientific notation, but -1. So this would be 98.7%. So very high probability that it is that flower. Now, if you remember from the data set that I showed you, it's sorted. And I didn't bother to scramble it because it makes this easy to see. But notice it's all iris setosa first, then iris versicolor, then iris virginica. Notice how at the beginning, the neural network is predicting all of the first class. And at some point, it'll break over. Yeah, now it's predicting more the second one. And then at some point, it'll break over and be predicting more the third one. And if we can also evaluate it. So if we look at y, which is what we want the output to be, that's the ideal output. There I'm just printing 10, but we could print all 150 of them. Oh, I haven't run that previous part, so it won't actually do that. But if I run this part, and it'll train it, then I'm going to let it go ahead and run for a moment up there. But we can get our predicted classes and our expected classes. You use Argmax to get the predicted class. What Argmax does is it gets ran for each of these, and it says, of these 3 input values, which of them is the highest, and give me the index. So if this one was the highest, it would be 0. If this one were the highest, it would be 1. And if this one were the highest, it would be 2. That lets you take, hopefully that's done now. Yeah. So that's done. So the input for this just shows you all the irises at the beginning, because this is the Y from that data set since it was not sorted. 1 for the first one, 2 for the second one, and 3 for the third one. So we can take all of those. If you take each of these and you turn that into Argmax, you're going to have all zeros because the first one was the highest up till here. Then the first one became the highest. And then finally the second with 0, starting from 0, obviously. And these are the predictions. Notice it lines up pretty easily. The neural network predicts with pretty good accuracy that. And you'll notice the accuracy is 97%. So there are a few of these, maybe one of these, that is incorrect. The rest of them are all exactly the value that we would expect. Now, we're doing a fundamentally bad thing with this neural network that is only acceptable to do in this class. We are evaluating it with the same data that we trained it on. So we fit it with all 150 cases, and then we evaluate it with all 150 cases. That leads to overfitting, which is a bad thing. We'll learn more about that in the next module, actually. And then if you want to ad hoc query it, it's like just fill in your own values for an iris that you just came up with off the top of your head. Just pick four random measures. This is how you would do it. So this would predict that an iris with that configuration that you gave it, it would say that that's possibly iris virginica. And that is all that I have for this part. In the next part, part 3, we're going to learn how to load and save a trained neural network. So you do all this work to create the neural network, you might as well save it.